Properties of transversals. Let me just start by saying you may notice, my geometry students, that the title of this section in the text, section 3.2, is Properties of Parallel Lines. That's not a bad name. I don't know that it's any worse than this one. But here's the reason why the difference. When we talk about the rules that we'll articulate in this section, they relate to transversals, which are intersecting parallel lines. Transversals intersecting parallel lines. So we could have named this properties of parallel lines, we could have named it properties of transversals. And it's possible to have parallel lines with no transversal. It's also possible to have a transversal with no parallel lines. But I've decided to call this properties of transversals because I think that what we're about to talk about really focuses more on the transversal than the parallel lines. You can disagree with me. Obviously, the authors of the text did, and that's perfectly fine. In addition to what I've already said, let me just say that all the rules, let me say it again, the rules that we'll be talking about deal only with transversals that intersect parallel lines. Okay? All of them deal with rules where I have a transversal intersecting parallel lines. You see I've drawn these two arrows on here. That's a symbol we use in a geometric diagram to indicate that lines are parallel. You may recall we have symbols like this which tell us that angles are congruent. We have symbols like that to tell us that segments are congruent. So these are just two new symbols that tell us that lines are parallel. There are three rules we need to cover, three objectives in this lesson, three rules you need to come out the other side with. I'll just state those rules before we get started. These are the names of the three rules we need to articulate. The corresponding angles postulate, the alternate interior angles theorem, the same side interior angles theorem. A bit of a mouthful, no doubt. Let me just say a couple things about these. First of all, you'll notice the first one's a postulate, an accepted statement of fact, which we should find to be intuitive. The last two are theorems. We'll prove the theorems. Remember, they're just shortcuts. The other thing I want to point out is that corresponding angles, alternate interior angles, and same side interior angles, are all phrases we're familiar with from the last lesson. We know what those are. In fact, the last lesson was devoted almost entirely just to learning what those words mean. So now we're going to develop some rules that incorporate those definitions we already went over. We'll start with the corresponding angles postulate. The corresponding angles postulate says that if a transversal intersects two parallel lines, then corresponding angles are congruent. Notice a couple things here. First of all, this is a conditional statement. And in chapter 2, we dealt quite a bit with conditional statements. So it is a conditional statement. And the way that we use conditional statements in reasoning is by the law of detachment. Right? We know that if we find a situation in which a transversal intersects two parallel lines, well, then we can conclude corresponding angles are congruent. Let's just take a look at that. Here we have a diagram in which the angles here at the intersection of the lines and the transversal have been numbered 1, 2, 3, 4, 5, 6, 7, 8. We have two parallel lines as indicated by the symbols. The corresponding angles postulate tells me that angle 1 and 5, those are congruent. Why? Because they're corresponding angles. 2 and 6 are congruent. 3 and 7, 4 and 8. This rule should be somewhat intuitive, as I mentioned earlier. Let's just check to see that it is. If I draw two parallel lines here, and instead of drawing a transversal, let's just pretend that the ruler, the meter stick, is a transversal. You'll notice that the corresponding angles do appear to be congruent. And as I rotate the meter stick, and you perhaps look at these two angles, we'll call them angle 1 and 2, you'll notice that angle 1 became acute and angle 2 also became acute, and they appear to be the same still. If I rotate in the other direction, angle 1 now appears to be obtuse, and angle 2 appears to be obtuse as well. So this rule is completely intuitive. It always makes sense if you just sort of take the time to look at it. That's a good thing for us. It makes it easier to understand. From here, we'll go and look at two theorems that actually find their genesis in this rule right here. First theorem is the alternate interior angles theorem. It says if a transversal intersects two parallel lines, then alternate interior angles are congruent. Notice again, it's in the form of an if-then statement. Also notice that the hypothesis of this rule is identical to the hypothesis of the corresponding angles postulate. Let's see if we can actually prove this theorem. Construct a diagram in which to work where the hypothesis of the rule is true. In order for the hypothesis of the rule to be true, we need a transversal that intersects two parallel lines. And there we go. So here's the hypothesis of the rule. We want to see if we can prove that this particular theorem works every time. To do that, I'll just number some angles in here. Here we have angles 1, 2, and 3. And we set up the proof just as we have in the past. So we'll start with some given. In this case, I can see that angle 1 and angle 3 are corresponding angles. That's a given. It's right there in the diagram. The next thing I conclude is that the measure of angle 1 is equal to the measure of angle 3. How do I know that? By the corresponding angles postulate. The next thing to do is focus our attention on angles 1 and 2 and ask how they're related. Angle 1 and angle 2 are vertical angles. And we know that that's a given also. So from there we can draw an algebraic relationship between those two angles, and that's simply to say that the measures of angle 1 and 2 are equal. That's by the vertical angles theorem. The final step is to simply look at this and say if the measure of angle 1 equals the measure of angle 3, and the measure of angle 1 equals the measure of angle 2, then by the transitive property, or by substitution, the measure of angle 2 must equal the measure of angle 3. So when you look at the diagram, it's important to know we don't have a clue about the measures of any of those angles. We have no idea what they measure. But there's one thing we can be absolutely certain of. Angle 2 has the same measure as angle 3. And that's the theorem, that's the shortcut. Sometimes we want to be able to reason from angle 2 directly to angle 3. And this particular theorem allows us to do that. Again, this is the alternate interior angles theorem. It says that if a transversal intersects parallel lines, alternate interior angles are congruent. The next rule we need to talk about is called the same side interior angles theorem. Once again, it is a shortcut. We'll prove it in just a moment by referencing the corresponding angles postulate. Let me just write it out first. All right, the same side interior angles theorem says that if a transversal intersects parallel lines, same side interior angles are supplementary. Notice the last two rules we're talking about congruence. This rule talks about the fact that angles are supplementary. Let's just see if that makes sense when we look at a diagram. To do that, I'll once again use the meter stick in place of a drawn transversal. When you look at this initially, if I sort of put the meter stick at a right angle to the parallel lines, I think you can see that that looks like about 90 degrees and about 90 degrees. So that makes sense that they'd be supplementary. They're also congruent, so we have to wrestle a little bit with whether the rule should be talking supplementary or congruence. But it turns out that if we begin to rotate the ruler to the right, you can see that this upper angle, I'll call that angle 1, and the lower angle, angle 2. The upper angle has become obtuse, while the lower angle has become acute. And so it's not difficult to imagine that as this one becomes more and more obtuse, angle 2 becomes more and more acute, to the point where their sum is still 180 degrees. If I rotate it to the left, angle 1 becomes more and more acute, as angle 2 becomes more and more obtuse. And so we find again that it's somewhat intuitive here, even, that the sum of these angles would continue to be 180 degrees. Let's just see if we can prove that, though, so that we can be absolutely certain I'm not just pulling things out of thin air. Once again, we'll start with a diagram in which the hypothesis of our rule is true. The hypothesis is that a transversal intersects two parallel lines, and we'll try to prove that angles 2 and 3 are supplementary. Angles 2 and 3 are supplementary. So here, let's get started. Number one, I'll start by looking at angles 1 and 3. I'll notice that angle 1 and angle 3 are corresponding angles. That's a given in the diagram. Number two, since they're corresponding angles, I know that the measure of angle 1 is equal to the measure of angle 3. How do I know that? By the corresponding angles postulate. The next thing I'll note is that angle 1 and angle 2 form a linear pair. That's also given in the diagram. The algebraic relationship then between angle 1 and angle 2 is such that the measure of angle 1 plus the measure of angle 2 is equal to 180 degrees. That's the linear pair postulate. The last step here is to make a substitution. Since the measure of angle 1 plus the measure of angle 2 is equal to 180 degrees, I can put the measure of angle 3 in for the measure of angle 1. And I find that the measure of angle 3 plus the measure of angle 2 is equal to 180 degrees. That's my substitution. So we've proven that these same-side interior angles they add up to, their measures add up to 180 degrees. Notice again that we don't have any idea what any of these angles measure. We don't have a clue. But we know that angle 2 plus angle 3, their measures that is, add up to 180 every single time. The last thing we need to talk about is probably just a few aspects of how these rules are actually applied. So let me just show you a couple diagrams and we'll do that. Here I have two parallel lines and a transversal that intersects them. Suppose that I know this angle measures 100 degrees, and I want to know the measure of angle 1. Well, it's pretty straightforward. The measure of angle 1 must be equal to 100 degrees because of the corresponding angles postulate. It says that if a transversal intersects two parallel lines, that's the hypothesis, it's true in this instance, then the conclusion is that corresponding angles are congruent. So this being a pair of corresponding angles, they must be congruent. Suppose then I also wanted to know the measure of angle 2. There's actually a couple ways I can get there now. I can get there pretty easily just by saying, hey, this is a vertical angle here, so it must be 100 degrees. I can also get there because I know that angle 1 is 100 degrees, therefore angle 2, by the alternate interior angles theorem, must also be equal to 100 degrees. The theorem gets me someplace, though, even if I don't know this is 100. Okay? If that information has been withheld, and instead I've been told that this is 100, I can still find the measure of this angle without worrying about the vertical angles theorem. The last thing that the rules help us to do with respect to the same side interior angles theorem is, if I want to know the measure of this angle, angle 3, and all I know is this angle over here, I can very quickly figure out that the measure of angle 3 is 80 degrees. Because I know that these two angles must be supplementary. That's pretty much the lesson in a nutshell. If you have any questions, shoot me an email.